Written by Bart Kosko in Fuzzy Thinking, The New Science of Fuzzy Logic, this book introduces a groundbreaking concept that challenges the traditional ways we perceive and process information. Kosko's work delves into the intricacies of fuzzy logic, a field that has revolutionized our understanding of computation and reasoning. The world is rarely black and white. In our daily lives, we encounter countless situations that cannot be neatly categorized into binary choices. Whether it's the diverse people walking down a busy city street or the myriad shades of green in a nature scene, our reality is a complex tapestry of gradients and nuances. We often navigate a reality painted in shades of grey. Consider the time lapse of a sunset, where the transition from day to night is not abrupt but a gradual blend of colours. Similarly, human interactions in public spaces are filled with subtleties and unspoken understandings that defy simple categorization. Traditional logic systems, with their rigid boundaries of true or false, struggle to capture this nuanced reality. Binary numbers, the foundation of classical computing, represent a world of absolutes. However, many real-world problems are far too complex to be solved by such a binary approach, leaving us grappling with confusion and ambiguity. Enter fuzzy logic, a revolutionary approach to computation that embraces ambiguity and uncertainty. Unlike traditional logic, fuzzy logic allows for degrees of truth, enabling us to model and solve problems that are inherently imprecise. This approach mirrors the way humans think and reason, making it a powerful tool for tackling complex issues. Fuzzy logic, inspired by the human ability to reason with imprecise information, offers a powerful tool for dealing with complex systems. Just as our brains can process and make decisions based on incomplete or ambiguous data, fuzzy logic algorithms can handle uncertainty and provide solutions that are both practical and effective. It allows machines to understand and process concepts like warm, tall, or fast, concepts that defy absolute definitions. For instance, determining whether a day is warm or cold isn't a matter of strict temperature thresholds, but a subjective experience that fuzzy logic can quantify and interpret. This essay delves into the fascinating world of fuzzy logic. We will explore how this innovative approach has transformed various fields, from artificial intelligence to control systems, and how it continues to shape the future of technology and human understanding. We explore its core principles, examine its inner workings, and uncover its widespread applications. From smart home devices that adjust settings based on user preferences to advanced robotics that navigate complex environments, fuzzy logic is at the heart of many modern innovations. Join us as we journey through the realm of fuzzy logic, a realm where ambiguity fuels innovation and complexity finds elegant solutions. Together, we will uncover how embracing the shades of grey can lead to breakthroughs that were once thought impossible, and how this paradigm shift is paving the way for a more nuanced and intelligent future. The roots of fuzzy logic can be traced back to the 1960s. This was a time of great social and technological upheaval, a period marked by rapid advancements and a questioning of established norms. Amidst this backdrop, a revolutionary idea began to take shape, one that would challenge the very foundations of how we understand and process information. Lotfi Zada, a professor at the University of California, Berkeley, was at the forefront of this intellectual revolution. Zada, an engineer and mathematician, was not content with the limitations of the prevailing binary logic system. He saw the world in shades of grey rather than in stark black and white, and he believed that our logical system should reflect this complexity. Traditional logic, with its rigid classifications of true or false, yes or no, 1 or 0, seemed inadequate to Zada. He argued that this binary approach failed to capture the nuances and intricacies of the real world. In reality, most situations are not simply black or white, but exist in a spectrum of possibilities. For instance, consider the weather. It is not just hot or cold, but can be warm, cool, or anywhere in between. To address this gap, Zada proposed a new approach, fuzzy logic. This was not just a minor tweak to existing systems, but a radical departure from traditional thinking. Fuzzy logic introduced the idea that truth could be a matter of degree rather than an absolute. It was a bold and innovative concept that sought to mirror the complexity of the real world more accurately. In fuzzy logic, truth values are not confined to the binary extremes of 0 and 1. Instead, they can take on any value between these 2 points. This means that a statement can be partially true or partially false, reflecting the real-world scenarios where absolutes are rare. For example, the statement "it is raining" can be somewhat true if it is drizzling rather than pouring. This system allows for degrees of membership in a set, meaning that elements can belong to a set to varying extents. For instance, in a set of tall people, someone who is 5'10" inches might be considered somewhat tall, while someone who is 6'5" inches would be very tall. This flexibility makes fuzzy logic particularly useful in fields where precision is difficult to achieve, such as linguistics, psychology, and artificial intelligence. The introduction of fuzzy logic was groundbreaking. It represented a significant shift in how we think about truth and logic. By allowing for partial truths, Zada's system provided a more nuanced and flexible way to handle information. This was not just a theoretical advancement, but had practical implications for a wide range of disciplines. One of the most exciting applications of fuzzy logic is in the realm of artificial intelligence and machine learning. By incorporating fuzzy logic, machines can process information in a manner that is more akin to human reasoning. They can handle vagueness and uncertainty with greater flexibility, making decisions based on incomplete or imprecise data. This capability is crucial for developing intelligent systems that can operate in the real world, where information is often ambiguous and incomplete. Zada's fuzzy logic offered a new lens through which to view the world, a lens that acknowledged the inherent fuzziness of our reality. It challenged the binary thinking that had dominated for centuries and opened up new possibilities for understanding and interacting with the world around us. By embracing the gray areas, fuzzy logic has paved the way for more sophisticated and adaptable systems, both in technology and in our broader understanding of the world. At the heart of fuzzy logic lies the concept of fuzzy sets. Traditional sets operate on a binary principle. An element either belongs to a set or it doesn't. A fuzzy set, however, allows for degrees of membership. Imagine a set of tall people. In traditional logic, a specific height would mark the boundary. Anyone above that height would be definitively tall. Fuzzy logic allows for a smoother transition. Someone slightly above the boundary would have a high degree of membership in the tall set. Someone even taller would have an even higher degree. Fuzzy sets, therefore, capture the nuances of language and human perception, acknowledging that concepts often exist on a spectrum. Section 4. Membership functions. Quantifying degrees of truth. Membership functions play a crucial role in fuzzy logic. They are the backbone of how fuzzy logic systems interpret and process data, allowing for a more nuanced understanding of information that isn't strictly binary. They quantify the degree to which an element belongs to a fuzzy set. This means that instead of an element being simply in or out of a set, it can partially belong to it with a certain degree of membership. These functions map input values to a membership value between 0 and 1, representing the degree of truth for a given element. For example, in a fuzzy set representing tall people, someone who is 6 feet tall might have a membership value of 0.8, indicating they are quite tall, but not the tallest. Various types of membership functions exist, each with a unique shape determining how the degree of membership changes with the input. Triangular, trapezoidal, and Gaussian functions are commonly used. Each of these shapes has its own advantages and is chosen based on the specific requirements of the application. Triangular functions are simple and computationally efficient, making them suitable for real-time systems. Trapezoidal functions, on the other hand, offer a more flexible approach by allowing a range of values to have full membership. Gaussian functions provide smooth and continuous transitions, which can be particularly useful in applications requiring high precision. The choice of function depends on the specific application and the nature of the fuzzy set being represented. For instance, in temperature control systems, a Gaussian function might be preferred for its smooth transitions, while in a simple on-off control system, a triangular function might suffice. These functions provide a mathematical framework for translating linguistic terms like warm, cold, fast, or slow into quantifiable values that machines can understand and process. This is particularly important in fields like artificial intelligence and robotics, where machines need to interpret and act upon human-like descriptions of the world. This translation is key to bridging the gap between human language and machine computation. By converting vague, qualitative descriptions into precise, quantitative data, membership functions enable machines to make decisions and perform tasks that require a human-like understanding of complex, nuanced information. Imagine a robot that can understand commands like move quickly or grasp gently. Thanks to membership functions, the robot can interpret these commands in a way that reflects the intended degree of action, making it more effective and intuitive in its interactions with humans. In smart home systems, fuzzy logic can be used to adjust temperature and lighting based on vague inputs like a bit warmer or slightly dimmer, providing a more comfortable and user-friendly environment. In automotive applications, fuzzy logic helps in adaptive cruise control systems where the car needs to maintain a safe distance from other vehicles. The system can interpret varying degrees of proximity and adjust the speed accordingly, ensuring a smooth and safe driving experience. In the medical field, fuzzy logic can assist in diagnostic systems by interpreting symptoms that are not black and white. For example, a symptom like mild pain can be quantified and used to suggest possible conditions, aiding doctors in making more accurate diagnoses. Overall, membership functions are a fundamental component of fuzzy logic, enabling a wide range of applications that require a nuanced understanding of data. They allow systems to handle uncertainty and imprecision in a way that mimics human reasoning, making technology more adaptable and intelligent. Section 5. Linguistic variables, bridging human language and machine understanding. Fuzzy logic excels in bridging the gap between human language and machine understanding. It achieves this through the use of linguistic variables. These variables use words or phrases to represent a range of values, capturing the imprecise nature of human language. For example, instead of defining temperature solely in numerical values, we can use linguistic variables like cold, warm, and hot. Each variable corresponds to a fuzzy set with a specific membership function. This approach allows us to interact with machines using familiar terms, making complex systems more intuitive and user-friendly. Linguistic variables are crucial for applications like fuzzy control systems, where human-like reasoning is required to manage complex processes.